this one. Okay.
Right?
Yes.
Should be. So speaking to here. You control from there.
Okay.
You speaking to.
Okay. Yes. And and this is the comprehensive rating index. You can, according to the index, then have a rank of the 17 models. Then you can decide which model I can use for this study area or the month. This is the result of the temperature yearly of each model. You can see uh, for this model, for bias, this model ranks #1, and for the standard deviation, it's this. So after it's the same, but then you got the comprehensive risk index. That means this model, according to all indices, it has better performance. The precipitation is the same temperature, but the result shows Ashford has a better performance to simulate the yearly precipitation of the study area. Then this is the monthly evaluation. You can see for this this is the higher of the number, that means the model is better. In this, like this one, this model shows a better result. So you can, according to this, decide in every month which model you should use to have a better result, predict or reproduce the historical period. And this is the precipitation. You can see they have a different performance. Some model maybe have a good performance for temperature, but maybe not in precipitation. And then, if you want to use all of the model, you can use model weighting of 17 GCM. This one, this is the rank of the model. You is the sum of the rank of the model, and this one is the model rank of single GCM. Then you have this one. Then you can calculate the weighting using this formula. In my case, I have 17 GCM, so you can calculate like this one, and after you can get a weight of the model. That means which should account for the simulation of result maybe better if you according to the weight calculate the average. Then, but even though you use the Gaussian, because the original GCM they have a big difference. So if you want a better result, you can do some Gaussian. For this method, I consider multiple years average at the monthly scale. And this one is precipitation. This method consider web days, also the bias, also standard deviation. This is the yearly Gaussian result. This is before. So this is the observation. You can see it has a big difference also for temperature. But after downscaling, then I use the average of 70 models. You can see they have a similar result. This is for precipitation. This is the wet days. You can see like whole months they have it is raining, but actually there's no much rain. Then after downscale, it shows acceptable result of the downscaling result. It's very similar to the historical period of observation. For the future downscaling, it's the same method to predict the future climate change. For temperature, consider bias, precipitation bias, and deviation, and white space. This is the temperature yearly change. This is the simple linear regression. You can see the R square is higher according to the radiative forcing. That means it, it it has a strong linear correlation between the temperature and the year. That means in the future the temperature will rise a lot. You can see also uh, the this is the GCM range. For each model, they have a big difference because the variation of each year is different. So I use the average of the 70 model to show a simple trend of the future change. You can see from according to the radiation forcing rising, the temperature will rise a lot according to different the higher radiative forcing and temperature will rise a lot. This is the precipitation. They don't have a strong linear correlation, but they also shows the upward trend. You can see the R square here. It also shows the trend, but not significant like temperature. This is the monthly change of future temperature and precipitation. Uh, you can see for forcing scenario, for temperature, they always show upward trending, but precipitation don't have a significant trend. So this month maybe you will have less water, maybe will cause drought or something like that because the temperature is rising, but the rain doesn't change much. And also for December, it's in the winter. I have this kind of results too. This is the monthly temperature change. You can see uh, it is rising for temperature, but according to the radiative forcing, whereas a lot you can see the difference between the color will show big difference, like according to the end of the century. This is the monthly precipitation. This is the station scale yearly change. For the historical, almost all stations show temperature shows upward trend, but the slope before it's near the high altitude, then it changes. For this scenario, change to close to the reservoir, and after it will distribute the study area. And for this scenario, this point have a high slope with a steep near the glacier high altitude. It's same as this scenario. This is the precipitation monthly. Let's see, for the high altitude, they don't have too much stations show trend. It's almost focused on the downward trend, downward area. But for this scenario, all stations show upward trend, and this scenario is similar to this one too, but the slope is different. And you can see the slope uh, will change too. For this scenario, the slope is here, and then it's close to this part. So you can see compared to the historical period, the trend from this downward trend and this part is upward trend, then change to rising precipitation.
So it's not then.
Precipitation, sorry, will keep rising. Thanks for watching.
Question.
I appreciate that you do not understand all of what you say. But my question is that the one told me that the downscaling is correct. That's correct. Can you tell me something more in context of which kind of downscaling
The statistical downscaling. Uh, for this one, this is the monthly scale bias of this is the GCM and this is the observation. I use the like multiple years average and I will calculate the bias. Then it will then you will get the bias of multiple years. Then you can calculate this is the daily. You can just minus the bias. Then you will get the bias factor daily GCM data of after downscaling temperature. And for precipitation, this one is the relative error of the precipitation. The closer to one, that means they have a smaller difference compared to the observation data. And this one means if equals to one, then you have a rain, and if it is zero, that means you don't have rain. So according to this, for this you have like a normal distribution to randomly distribute the precipitation in the monthly scale. Then you will, it's also according to the multiple years. First, you calculate if this is the 1.5, that means the precipitation of the GCM is higher, so you need to make it a little bit less. If it's less than one, you need to make it rise a little bit. Then this one calculates it if for this month if they don't have rain or they have rain, it is according to the multiple years average of the historical data, and then it will distribute it to the months. Then you got the bias factor precipitation. You will understand.
Okay. It's some fact that I'm correlated in time.
This one is a factor you can use this. This is a normal distribution. It will like according to normal distribution to have if you have 30 days, it will have 30 the certain values close to zero. Then you can calculate uh, this this one simplify is to uh, this one is to you can have this one depends if the precipitation is too high or not high. This part is according to the historical uh, observation of the white space. So this is like the precipitation, and this to decide the white space. Then according to this, it will like distribute the precipitation randomly. It's like the precipitation historical is like 30, and this will have 5 days of rain. Then but the GCM is not correct. Then it will according to the value to distribute the days into 5 days. Then it will have a similar variation. This one is the standard deviation. It will have a standard deviation. then it will distribute the precipitation in 1 month, like only 5 days. That will be the same to the historical period.
The precipitation doesn't stop.
It includes snow. It's total precipitation, not only rain.
And also the model is about
Yes, it's the same.
meaning it is flooding to how your approach the used
Uh, for for now, I'm still doing some research of the climate extreme that will have some like the more specified some events. They have a big rain or something. This is the overall evaluation of the downscaling results. After I can use this kind of data to have some indices. That means the heavy rain maybe will cause flood or something like that. Then I can like which year the precipitation is not normal or too high or too low. Then you can have a warning of maybe that year will happen something. And there are standard models. Maybe they have different results, so you can have a different result. Then maybe this will happen. Then be careful, something like that.
foundation mentioned seven
Yes.
quite explain
Because now I just want to use show like the overall mm, overall result. I didn't like show like for each model because there are some here I show so this I don't see because this one you can see here maybe this model change like this and this model change like this. Maybe they have a different result, but for here I only show the average of the 17 models.
then here's the name of the
Yes, yes. This one is not waiting because it's after downscaling. So I only use the simple average of the 17 models. If you didn't do downscaling, you can according to the weight to just use the the original data output.
go back
We
that one with the damage and yeah. This picture basically says that we cannot see the mean is a smooth so much of it, but if you see the open model, force this challenge but with the impact of the different and then you get another last energy now, but you cannot use the in order to take because it's basically moving special for problems that was moving the final question. Linear trend of
It's just to show maybe the temperature between the data and the year. They have a strong linear correlation. The point is very close to time. The correlation, still, original very high temperatures. Probably the assumption of the scenario for the present.
over points are the issue.
Yes,
project. So, the additional focus is that this is the outcome of the models. Right? So this is just a confirmation that the models provide consistent outcomes. But the representation is much more better.